So, hello everyone, thank you for being here today. I'm glad to present this work again, which appeared in our collaboration with Guy and Andrea almost a year ago. And now it has more or less its definite shape, I guess, and I'm very happy of the results that I'm going to present, and it opens really very interesting avenues. So, what were our initial motivations? One of them is something called Hilbert space fundamentalism. So the expression emerged in a 2019 paper by 𝗔𝗯𝘀𝘁𝗿. Look at you can't see very well, but look at the title of the paper, Mad Dog Everettianism. But in fact, some pioneer ideas can be found maybe in Federico Piazzia's work, 2010 already, maybe even before, earlier, because it's a very general attitude. It's not a well-defined concept, but HSF is the attitude of hoping to see a lot emerging from very little, especially in the context of quantum mechanics. HSF people want to recover a lot of structure, for example, typically a space-time, a tensor product structure, notion of locality, subsystems, and whatever, only from basic quantum ingredients such as a Hilbert space, a Hamiltonian, possibly a state. But another motivation is quantum mereology. It's a booming field of quantum foundations at the moment. And the main aim of quantum mereology is to be able to identify a TPS, that's a product structure, in a big Hilbert space. So there are a lot of proposal criteria, so on. Some of them use, I don't know, locality, causal decomposition of unitaries. Some of them look at the form of the Hamiltonian, as we see in a moment in this talk, but there are many other ideas. But there are a lot of different reasons to be interested in what I'm going to talk about, even from the theory of decoherence. 𝗔𝗯𝘀𝘁𝗿 coined this quite famous expression, the looming big problem of decoherence, by which he means the fact that when you do decoherence models, you have always a split of the Hilbert space into a system and environment. And 𝗔𝗯𝘀𝘁𝗿 said, okay, that's all good, but this distinction seems arbitrary. How do we know which are the systems and which are the environment? And if you change completely the TPS, then everything will look completely different, and decoherence is not guaranteed. So 𝗔𝗯𝘀𝘁𝗿 posed this question of the role of the TPS already back in the end of the 1990s. Other reason to be interested, quantum gravity, of course, because if you're interested in how to see the emergence of a preferred TPS, and the TPS, the tensor product structure in quantum mechanics, encodes the very notion of locality. Maybe you have already some hints at let's say some building blocks of an emergent spacetime. Quantum reference frame also more recently. People doing QRFs seem to be more and more interested in the so-called relativity of subsystems. But the TPS is the very division of the universe into subsystems, and it seems more and more clear that the TPS is frame dependent in the QRF works, and so this is yet another reason to be interested. And the last one is the measurement problem. So Guy, one of us, has a paper about that, about trying to explain the uniqueness of outcome based on some TPS thoughts. So you can have a look at this paper. So the big question is of HSF, but also quantum mereology. In this case, in this talk, because I told you there are many other avenues, but the big question we are going to study here is, can a Hamiltonian uniquely select a TPS? This was the very topic of last week's talk. But I will also add another one, the possibility to add a state. And we will see it's very important because in Cotler, Ranard, and Pennington's paper, the situation is different. They don't allow for upside. So the main object of surprise that sparkled our work was this apparent conflict between these two theorems. So the first is the one that we discovered last time by Daniel's talk, And the second is a theorem by Stoica. I don't know if Christy is online. I hope so. So the first theorem says, yes, remember, we can select a TPS under some big assumption, but let's not go through that. But in general, if there is a TPS that makes the Hamiltonian K local, then this one is unique. And so therefore you can select a unique preferred TPS only via the data of the Hamiltonian, and in fact only via its spectrum. But Stoica said in a series of papers, started like in 2021, but there are many other papers released about that. And his main point is to argue against HSF, Christie. And he says, no. There's a theorem showing that, no, you can never select uniquely a TPS by Hamiltonian. And in fact, he makes an even stronger claim in a later paper where he says, no, you can never select any structure, not only a TPS, any kind of structure by a H, and even by H and psi. So it seems to be two clearly conflicting theorems. So let's try to disentangle all that. Yeah.
So when you say H and psi, what is
a state? So you have a Hilbert space. H would be a Hamiltonian operator, Hamiltonian, and psi is just a space and a vector. Sorry, a vector state, unit vector. And so this is the basic data you are used to have in quantum mechanics, right? And using this data, can you select, for example, a TPS? And so Daniel yesterday.
The ground state of H, or
it could be the state at time 0, or the present state, or you could imagine because H, in fact, the full trajectory of psi through time, so it's the history of the universe or whatever. If you are a many worlds advocate, it's very appealing, of course. That's why the very notion of HSF was, and I guess the expression was coined by Carol and Singh, who are hardcore Everettian. I remember Mad Dog Everettians. But you don't have to be a Mad Everettian to be interested in this question. But yeah. So in fact, the two theorems are not incompatible. This is one of the aim of the talk to explain why. In a nutshell, the first one has been misinterpreted and misused, and it will be very interesting to look at the misuse to understand the true statement of Cotler et al. And Stoica's theorem, the first one is valid, the stronger one is not. And solving this tension, in fact, so take it as a case of study, because in fact we go much further, and we will really delve into what is geometry and what are the structures in a geometrical space, especially here in the case of quantum mechanics, but in fact all physics, all theoretical physics is phrased in terms of geometry. So you will see we can really go quite far with this. So I'll go very quickly through the two first sections, because it's just a review of the theorems, and we had already last week's talk, and I want to keep time for the last session, which is the main dish and our original insights. So let's go. So just very quickly with the definition, because we had the talk last week. So for all the talk, we fix integers n, di, indexed by I, ranging to n, and a Hilbert space of finite dimension product of the di. So of course, what we have in mind is to divide the Hilbert space H into n factors of respective dimension di. And I have to apologize to do finite dimension, but we all do that in quantum information theory. I'm really sorry, and this is clearly a weakness of our approach. So definition of a TPS as exactly the same as Daniel used last week. So a TPS is an equivalence class of isomorphisms that factors a Hilbert space into n factors, and you take the equivalence to be the fact that these two isomorphisms just differ up to what we call local unitaries, meaning unitaries applied on the different factors, and possible permutation as well. And so when you have a TPS, any operator, but so let's fix once and for all a Hamiltonian operator that we call H, and we will say this is the Hamiltonian, but just take any operator, it doesn't have to be anything special. And so when you have a TPS, you can always decompose Hamiltonian operator this way. So fix some bases in the different factors of the TPS, and you can look at how many pairwise interacting term you have at most. So the first one would just be an identity, and then you have only the factors that acts on one factor of the TPS. And when I write OI alpha, I understand it as OI alpha on the I factor and identity everywhere else. And so the sum, you see, I sum all the terms with only one interaction term, two of them, three of them, etc. And so we have a notion of K locality when you have a TPS and you have a Hamiltonian H, you can say that the pair HT is K local, or maybe that the TPS makes the Hamiltonian K local or something like that. If there exists a choice, so yeah, forget about that. If the decomposition above involves at most K non-trivial operators. So it's exactly the notion of K locality that Daniel expressed last week. But I want to stress something very interesting. So Daniel said it last week a bit. But for me, it's very important for us. We wanted to emphasize that in the paper. So K locality, the name can be a bit misleading because it really has nothing to do with what we usually call locality in physics, especially space-time locality. So of course, it's an appealing criterion. It's cool to say, yes, there is only one TPS that makes the Hamiltonian K local. I agree. And so in the Ising model, we have this example in mind all the time. And so in the Ising model, for example, the K locality coincides with space-time locality because in the nearest neighbor Ising model, for example, because you have indeed only interacting terms between neighbors. And so it's two local, for example, and these two locality encapsulate something of the neighbors of the topology of the space. But that's not true in general. Think of I take Ising nearest neighbor model. Yeah.
I would say that Ising model or K-local interaction means that it's not on a line, but on a, for example, graph.
On a graph,
for
true.
Local.
But it's a graph that when you do it in general, when like actual physicists are studying the Ising model, this graph is in fact just a sprinkling of the true underlying space-time. So they just imagine that you really have a network of atoms or whatever, or spins, and then they draw a graph from the space-time background which is there. But imagine now an Ising model, nearest neighbor model, but I also had a crazy interaction term with the term z and term z plus 1,000. So it's still too local because you would still have only two systems interacting at a time, not more. And yet it has nothing to do with the underlying background space-time notion of locality. And another example, just think of Newton or Coulomb interaction. It's obviously too local, but because you never have more than two systems interacting, but it's famously known as infinite range interaction. So far from being a pointwise type of interaction as we usually think of local interactions. By the way, I don't think anyone in this room has ever seen a Hamiltonian more than two local. The Hamiltonian we really use in physics are just two systems interacting at a time, and I've never seen more. Maybe in QCD or something, but honestly, in routine Hamiltonian, we have only two locality, in fact. And conversely, a QFT, well, it's always space-time local by construction, because by construction you have this notion of fields interacting at points. So no matter K, so you can have like billions of fields interesting at the same time, it will still be local. So you see, really, K locality has not much to do with space-time locality. And by the way, I wanted to stress this interesting result by Nicolas Loiseau and collaborators. By numerical simulation and computation, they found that in fact most Hamiltonian are approximately too local in some TPS. So of course, Daniel's talk last week showed that when you impose exact K locality, then you have an algebraic thing that happened that makes it unique. But if more physically reasonably you ask only for approximate locality, then everything is too local, and the question becomes trivial. Okay, so this is super important. Really this is why I want to present Cotler's paper, because it's super important. This is the line of the paper that literally everyone missed, including ourselves for sure. I will come back to the history of the paper in a moment, but it took us so long and some discussion with Christy and Daniel to understand that. There is the line in Cotler's paper introducing this global unitary equivalence. And in fact, all the paper has to be understood in up to global unitary equivalence. So they say that something is unique, they stick up to this unitary equivalence. And so it appears somewhere in the paper, and then it's kind of, you forget it. It seems hidden, and that's why then everyone struggles to understand and interpret correctly the result. And so mind that when h equals h bar, this global unitary equivalence can be reduced to something. And in the paper, the author do it a bit, to me, a bit fast. And we will see later a proposition that allows to prove why this definition is truly equivalent to the first one when you reduce to h equals h bar. Then the notion of showing that there is a unique TPS that makes the Hamiltonian local amounts to this definition of k-duality, to say that, okay, suppose you have two TPSs. We will call them k-dual if they are not equivalent with respect to h. However, both of them make the Hamiltonian local. And Cotler et al. Aim is to show that there are no duals in general. Therefore, the TPS is indeed uniquely selected by the Hamiltonian, because you don't have two inequivalent TPS that looks the same for the Hamiltonian. And so the example, I think Daniel gave it, a famous example is the Jourdan-Wigner transform. So he called it another way. I didn't know the other way transform he called last week, but whatever. When people study the 1D Ising model, they often use this Jourdan-Wigner transform, and it really changes the TPS. However, the Hamiltonian is different, but it's still too local.
This is what Cranmer's 1A is, I think.
Yeah.
It's not the same as Jourdan-Wigner, because Jourdan-Wigner matches fermions.
Okay.
Yeah,
okay.
People call it Jourdan-Wigner variant that is in fermions.
Okay. Okay, thank you. That's one. Okay. And so after a very, very, very hard proof and a lot of hypotheses, but we went through them last week. So Cotler's theorem is that yes, the almost all k-local Hamiltonians do not have k-duals. Therefore, if there is a TPS that makes the Hamiltonian local, then it is unique. Up to many hypotheses, and also one assumption is impossible to show, and so I have to rely on numerical simulation to say that yes, this assumption is plausible. Okay, let's go through the Stoica theorem very, very quickly. Stoica, here's I think the shortest punchline we can say to summarize Stoica's results. If a Hamiltonian admits a TPS in which it is k-local, then such a TPS is not unique. And he has a method, a machinery, to generate a lot of TPSs. Once you give me a H and a NH and a T, such that they are k-local, he has a machinery to generate a lot of them, distinct TPS, but distinct and not in equivalence. So this is now we will start to understand why the two results are not incompatible, because they are not saying the same thing, because they are not considering structures in the same way. And when Stoica says the TPS is not unique, he thinks of it in a strict sense, meaning that really T is different from T prime. Whereas remember, for Cotler et al., it was up to this global unitary equivalence. So I will try to be careful, and in the paper we really try to careful of the words. We use the word distinct for strict uniqueness, strict difference between structure and inequivalence when it's only considered up to the global unitary equivalence. And so Stoica's theorem follows from two lemmas. So quite easy to understand. The first one is to say that k-locality is a unitary-invariant property. It's something, a geometrical intrinsic property. So if you have a k-local pair and you rotate everything by unitary, it's still a k-local pair. It's just like being orthogonal or something. And lemma 2 says that in a nutshell, it says that the Hamiltonian has more symmetries than the TPS. meaning that you can find unitaries that stabilizes the Hamiltonian and not the TPS. And so then it's obvious that the theorem follows from these two lemmas, because suppose you have an H and T, so a TPS that makes HK local. Well, you can find a symmetry of H which is not a symmetry of T, apply it, H has not changed, but the TPS has changed by construction, but it's still a K-local pair because it's a unitary invariant property. And so you have found a new TPS that still makes H K-local, and a new meaning distinct TPS, but clearly not in equivalence, because everything is obtained precisely by acting a global unitary. So it's precisely equivalence. Good. I will not show why, but in a nutshell, the first lemma is true, obviously, because the coefficients in this decomposition one are Hilbert-Schmidt scalar products. So they are obviously unitary invariant things. So being 0 after rank k is obviously preserved by unitary. And so why H has more symmetries than TPS? In short, it's a dimension counting argument. And there is a little subtlety at some points but you have to look at commutative subgroup and so on. But all the ideas in the paper, we reviewed that and tried to make the proof rigorous and compelling and concise, but all the ideas were already in Stoica's paper. And Stoica gives so an interesting thing, but what time did you do? Yeah, okay, let's keep time for the rest. So that's interesting, but whatever. It's not the hot topic of today. So this is now the main dish. This is now the most our novel approach to try to understand to draw the lessons of this situation, understand which theorem is correct or not, how do we use this theorem, and how to go further, and also how to solve the big question of HSF, which was still unsolved. So the two theorems are not incompatible because, as I said, they have different. Oh yeah, sorry. A little pause. I want to tell the story of the paper. So incredible story. So we started to work on in April or something, maybe in March. Some discussion already previously, but by June or something, we had a first draft with all the review of Cotler, Stoica, and we were convinced that Stoica had shown Cotler's theorem wrong, and the proof is so incredibly difficult that it's plausible that might be a mistake, and Stoica is so clear and compelling. So we were really convinced, and then I was in a conference in Gdansk, the foundation conference in July, and at some point, just a few weeks before, I had uploaded on the archive a little paper about TPS, but really not as important, not really simple result, nothing incredible. But in the introduction, I mentioned the fact that Stoica had shown Cotler's result wrong. And so during the conference, I received a nice email by Daniel Ranat, so very, very polite, and he told me, yes, I've seen your paper. So in the introduction, you say that Christie has shown our result wrong, but I don't agree. I mean, we have a proof, etc. And I said, and so I was overwhelmed by the conference, too many social interactions, so I couldn't reply immediately. But Christie was in copy, and so Christie replied, and he said something like, "It's true. I'm not saying that your result is not true, but everyone misunderstands it." And so they started debating in my mailbox, and at some point they were even apologizing for including me in this debate, but they didn't know I was precisely working on that. So it was really perfect for us, because then we had a long email exchange, which helped us so much to improve our paper, because it was in fact it was very bad, the first version, and thanks to this email exchange, now we really knew what was the question to solve and what they themselves didn't know yet, and it helped us, to disentangle who was right and wrong. Funny story. But so now this section is about really going further this July debate in my mailbox. So for Cotler et al., a structure acquires its identity relationally, meaning that only unitary invariant things are meaningful. Whereas for Stoica, it is absolute, meaning that t and ut, in, for example, the time evolved t, are said to be distinct, regardless of whether there is anything that can really distinguish them, any unitary invariant meaningful property. So a good way to understand that is to look at the misuse of Cotler's theorem. And most people, of course, including ourselves, before this debate, this July debate, had completely missed this global unitary equivalence relation that has to be put on top of all Cotler's paper. And so everyone thought that the result was give me a Hamiltonian, I can produce a TPS, or maybe if there exists, then it is unique. In the absolute sense, everyone thought that there is really unique and not up to this global unitary equivalence, and therefore it leads to misuses. For example, a famous in this field, a famous attempt is 𝗁𝘀𝘁𝗁 2018. So it seems to be 1 year before Cotler's paper, but in fact, I guess the peer review took a long time and so on. But so this paper by 𝗁𝘀𝘁𝗁 is really based on Cotler et al. Paper. And they try to build an emergent space. How do? They say, give me a Hamiltonian and a state. Then they say, I use Cotler's theorem to produce a unique TPS. And then they say, and now I use the psi, I compute the mutual information of this psi with respect to the TPS given by Cotler's theorem. And depending on how much you have mutual information, they say you are closer. The closer you are, the more information you share. And so they build the proto metric on this, topology metric from only a TPS and the mutual information. And so it's an attempt to have an emergent spacetime, very interesting. But it's wrong. It's simply wrong. Why? Because Cotler's theorem gives you only an equivalence class of TPSs. But an equivalent class, remember, taken on all the pairs HT, but not on the triplets HT psi. Therefore, the psi the construction might depend on the representative you take for the TPS. So Cotler's theorem gives you an equivalence class of TPS. They have in all the TPS have the same relationship with respect to H, but they may not have the same relationship with respect to psi, especially the mutual information may not be the same depending on the representative you choose. And so the construction is flawed. Yeah.
You have a H, Hamiltonian, TPS, and the psi. And then you apply a global unitary to all of these. You just move your head around in the Hilbert space.
Yeah.
But it is a collaboration.
No, what's your question? Yes, but it's not what they do. 𝗀𝘀𝘁𝗁, they fix once and for all a TPS, an H and a psi. They fix them once and for all. They think of them as absolute objects. And then by Cotler's theorem, they build a TPS, forgetting that it's only an equivalence class. And they look at its relationship with respect to the fixed psi. But depending on the representative, psi may have different mutual informations between the factors.
But I do not say that you have a TPS, a member of this class, 1.
Yeah.
And then for that, to describe reality, you use this psi. But then if you change the TPS, then you change the psi with it.
No, that's not what. No. They fix H and psi once and for all. Then there is no more notion of applying a global unitary in their construction. I mean, maybe we become clearer in a slide afterwards, because it's important to see that the equivalence class with respect to a unitary applying on H and T is not the same as the equivalence class when you consider the triple HT psi. And Cotler's theorem is about the first one, but 𝗀𝘀𝘁𝗁 used it as though it was about the second one. Now, the big question is, okay, we have 2 theorems. So now we know the first is rational, the second is absolute. Okay, that's very good, but which one should we trust? I mean, we are physicists, so what should we believe? Should we consider structure as Cotler or as Stoica? What's the more interesting for us? And so an important step of the paper is to argue for this, for the fact that in physics we should be relationalists. Why? Because think, for example, of Stone-von-Neumann theorem. It's a very famous theorem at the foundation of quantum mechanics, which says that, okay, you should represent Heisenberg algebra, H and P, as operators in the Hilbert space. And Stone-von-Neumann's theorem tells you there is only one way to do that, up to a global unitary equivalence. So the theory is well defined. You don't have two possible ways to represent X and P in the Hilbert space. And if you have two structures that differ up to a global unitary equivalence, they will yield, by construction of quantum mechanics formalism, they will yield the same predictions. So they are the same theories. For an experimentalist, it doesn't change anything. So there is, in fact, only one structure. And when you want to say there is a unique structure or unique theory in quantum mechanics, you should be a relationalist. By the way, it's also the case in math, because especially since the advent of category theory, one of the most the first non-trivial, very important result in category theory, at the foundations of category theory, is Yoneda's lemma. And Yoneda's lemma tells you that, morally speaking, the objects acquires their identity through their arrows. And the arrows are the relation they bear with respect to other objects or with themselves. So it's really, identity appears through your interactions and relation with the others and yourself. Good. Now, let's try to formulate mathematically a formalism that helps us deal with this question of the uniqueness of emergent structure. So now we'll go to something much more general than just TPS. And then in the end, in the last slide, we'll come back to the case of study of the CPS and solve the important question we have to solve. So how do you say that a structure emerges from a first one? First, two steps. First step, you specify exactly what are the kind of input structure and emergent structure. So typically, input could be H, emergent could be TPST. But if your input is H and psi, it will be another mathematical question to solve. So it's really important to say what are your input structure, what are the structure living in your Hilbert space. And second, you want to be able to find a unitary-invariant property, think of K locality, for example, such that it selects a unique pair of structures up to global unitary equivalence. So you want to find a unitary-invariant property that selects a unique orbit in the pair of structures. That's exactly what Cotler theorem do. They say, take a H, take a TPST, and look, K locality selects a unique structure up to global unitary equivalence. Now, here is definition introduced by Stoica. It was very complicated in the first papers. He tried to define the notion of kind of structure by tensor equation or inequation and so on. So the definition is interesting, but it takes like 2 pages, and I tried to extract the essence of it. And I think the only thing you need to do what Stoica proposes is to define a kind of structure as just a set on which you have an action of the unitary group. And then I add a new version of the definition. I would say that a kind of structure is determined if, moreover, the action is transitive, meaning that, in fact, there is only one such object. So now a lot of examples so that you get used to it. An example of kind would be the kind of vectors. So the set of all vectors. So it's just the Hilbert space. That's clearly a set on which the unitary group acts. You have the kind of Hamiltonian operators. You still have an action. You have the kind of representation of a Lie algebra. When you have one Lie algebra, you can, of course, rotate it by unitary. Kind of TPSs. Now, example of determined kinds. So kinds of structure in which there is, more speaking, only one structure, and all of them are just related by unitary. Well, unit vectors, you can always join a unit vector to another one by an appropriate unitary. So there is only one unit vector, if you want. Hamiltonian operator, given spectrum, there is only one. You can, at least in finite dimension, you can always rotate a Hamiltonian to another, and you just choose the eigenbasis, to map the eigenbasis to the other. Now, representation of the Heisenberg algebra. This is a determined kind. There is only one representation of the Heisenberg algebra. What is this result? I just said it 5 minutes ago. It is von Neumann theorem that tells you that this is a determined kind. Another example is just, yeah.
Are you saying that the first 4 examples of kinds are actually not determined?
Yeah, not determined. If you take a unit vector and a 2 vector, no a length 2 vector, no unitary can possibly map one to the other, of course, because the norm is preserved. If you take a Hermitian operator and another one which has a different spectrum, you have no chance to map one to the other. So for sure, the spectrum has to be conserved. And then the fact that it is a determined kind is the fact that, in fact, the spectrum suffices to make it only one object. Another another example of kinds is the families of n vectors. You just take n vectors, but you impose the pairwise scalar products to be Gij. So Gij would be the Gram matrix in this case. If you impose the Gram matrix, then all families of n vectors are related to unitary. It's not entirely trivial to see it, but you can prove it. And TPSs, if you fix the number of factors and dimension, you can always do it, because TPS is entirely defined by a choice of orthonormal basis properly labeled, and so you can always map an orthonormal basis to another. In fact, it's just saying that orthonormal basis is a determined kind, and this is a special case of the line before with Jij being the identity. So when you have two determined kinds, so two set of structures in which there is, morally speaking, only one object, the product kind is not determined. So for example, there is only one Hamiltonian with given spectrum, there is only one TPS with given number of factors, but does the pair HT, the set of pairs HT, is it determined? Generally, no. Generally, you have more orbits in the product kind, or you can have different orbits in the product kind, even though you have only one in each structure. And so it's always possible to, or can be possible to restrict the kind in order to make it determined. So this is an important example. Take the pairs H psi. So even if you impose the norm of psi and the spectrum of H, so you have two determined kinds, but when you take the product kind, then it's not determined, because there are many ways for psi to stand with respect to H that can be distinguished up to that can be distinguished even up to unitary equivalence. And so what you can do is to say, I impose the spectrum of H, but also the eigenprojections of psi, the norm of the eigenprojection. And this becomes a determined kind now. So now there is only one way up to global unitary equivalence to choose an H and a psi with given spectrum and given eigenprojection. It's not super hard to show. So you see what we do, we add a new property and it selects a unique object. And so in fact, remember that will be useful. The unitary group acts not only transitively, so it's determined, but also freely on this kind. And that will be important.
That's trivial.
So the stabilizer is trivial, so it means the action is injective. So now we can define the notion of relational uniqueness. Two kinds, take two determined kinds, and P a unitary invariant property on the products. And we say that P determines the product kind if this property holds exactly on one orbit, if it selects only one object within this variety of orbits in the product kind. And so now we recover the definition that I gave one slide earlier. We are looking for unitary invariant property P's that selects objects up to a global unitary. And so we select a unique orbit. And if you find such a P, then you can say you have uniquely characterized an emergent structure. So again, think of Cotler's theorem. You have H, you have the TPS, you impose K locality. Well, you have selected a unique TPS out of H. Example. That's why the section is entitled Insights for Invariant Theories. It's a wonderful sub-branch of geometry, invariant theory, in which you have this notion of complete set of invariants. And what is the complete set of invariants? It's just a family of unitary invariant properties. I mean, functions, a real valued function, like scalar products or whatever, but you have a list of them sufficient so that imposing the values of these invariants selects a unique orbit. It's exactly the same notion. And recall the kind of n vectors with given gram matrix, specifying a gram matrix selects a unique object. It's a complete set of invariants. Or think of the example just I gave before, where you have h psi and you impose the eigenprojections. This selects a unique structure. So this is a complete set of invariants. The k-locality property on the product kind Hamiltonian cross times TPSs. This is an example of property that determines the product kind. How do we know that? This is just a reformulation of Cotler theorem. And yeah, don't recall that. We haven't seen this proof. But... So we need a result to help us. We need a result to help us simplify the problem. Because when you have, it's not easy to picture the orbits in a product kind. Even if you see how are the orbits in the first kind and in the second, it's quite hard to imagine, two objects rotating at the same time and how are they with respect to each other. So so what can we do? We can rotate everything to a fixed structure in K0 in the input kind, and just simply look at where the emergent structure lands. And you can always, since you work up to your global unitary, you can always rotate to a fixed one because the kind, remember, it's the unitary group acts transitively. And so now this is, to me, the most important result of the paper. Although, of course, most people will be more interested probably with the theorem that is coming afterwards, proved using this proposition because it was the question of HSF. But for me, in the long term, this is really the results I want to investigate more. So take the S0, this fixed K0 structure. The proposition says that you have bijection between the orbits in the product kind, so this is the top left set, to the quotient between the emergent kind, quotient up to the stabilizer, and this time not to the full unitary group, but only the stabilizer of S0. So meaning that if you want to study the orbits in the product kind, you can just as well study the orbits in the emergent kind up to a new symmetry group. And this bijection is interesting because it commutes, it makes the diagram commuting, meaning that it's compatible with the property P. So suppose you have found a property, unitary invariant, that selects, let's say, 4 orbits in the product kind, then it will be exactly true on 4 elements of the new quotient. And so everything that happens in the product kind, you can just see it by fixing the first structure and looking at what happens in the emergent kind. And for example, now if you want to find a property that determines the product kind, you just look at a property such that the set of emergent structure that makes the property true, with S0 as an input, contains only one element. And so why is it interesting? Because it reduces the problem to the point of view of S0, right? So you become S0, and you see where is SE, how does ST stand with respect to U? And in a way, with a lot of quotation mark, you can think S0 is as an imperfect reference frame with an imperfect observer with respect to the Hilbert space, looking at another structure. For example, I'm a Hamiltonian. I'm looking at the TPS around me. What do I see? Which unitary invariant things can I grasp? So if I'm Hamiltonian, I have my eigenprojections. For example, I have my eigenbasis. I can try to see things. And so, if your stabilizer, if you are a structure and your stabilizer is non-trivial, well, it means that you are an imperfect reference frame because you see structures up to this stabilizer. And for example, a Hamiltonian cannot distinguish 2 TPS up to a symmetry of H. And that's exactly the point that Stoica made. And so, yeah, to put it like, in a funny phrasing, maybe we could say that the structure S0 sees the first person point of view of this structure is a coarse-grained Hilbert space with a kind of effective symmetry group. Well, what I wrote is not really a symmetry group, but because it might not be a group, but whatever. And oh, by the way, this is well, I don't want to dwell on that too much, but remember in the beginning I said Cotler et al. They reduce the definition to equivalence with respect to an H, and I said I was not so happy in the paper how they go a bit fast with that, and I think this proposition is the good way to justify that. But let's not go too much into the details. And corollary, when suppose now the stabilizer is trivial, so the action is not only transitive but also free on K0. And then the problem is when you want to determine the product kind, you just have to find. You can think absolutely, and you just have to find a property such that there exists a unique emergent structure. Now, unique in terms of Stoica, unique absolutely, because you are in the special case of freely, so the stabilizer is trivial, and so the orbits are mapped one-to-one with the object of Ke. And that's good because the HSF example of kind I gave previously, remember I said the action is free, so the stabilizer is trivial, so we can use this corollary. Because now we want to go back to the HSF question. So that was just, a mathematical adventure towards abstract notion. But now let's go back to the TPS question, the HSF question, and let's apply this abstract formalism. We need a new theorem because Cotler theorem is not sufficient for HSF. Just look at Kao and Singh attempts to build an emergent spacetime. It's not just not the right theorem to use because it depends on the choice of representative of T that you take. So we need a new theorem in which the input structure is not H, but H and psi. So now the question is, can H and psi determine uniquely a TPS? And so Stoica made a claim. Stoica said, in the proof also, there is a theorem, no unitary-invariant property is very general, very abstract, on H and psi can determine a structure, any kind of structure. And I say no, this is not correct, Christy. I'm sorry, and I think I know where there is a mistake in the proof, but basically he doesn't treat H and psi exactly on the same footing. The first is treated absolutely, the second relationally. If I have to explain the detail, it will be too long. But in a nutshell, this is the problem. And so, so the question is, can we determine the product kind K HSF, so H psi and TPS? Can we find a unitary-invariant property, just like K locality, that selects a unique pair of structures, and therefore, from which you could say, I can select a unique TPS out of H and psi? And the answer is yes, we can do it. So this is the theorem based on using the corollary, the previous corollary, plus a few other ideas. So you can find a unitary-invariant property that determines the product kind, provided the spectrum is non-generate and the projection non-zero, but it's not so much. And so you can find a property that selects a unique triplet up to global unitary equivalence, but again, it's not the same unitary equivalence as Cotler's. Sketch of the proof. If you want to see, you can ask questions. Yes.
Should I think of this H psi pair as the Hamiltonian, and psi is a state that it will get to somewhere in its time evolution?
Think of it as the initial state.
Yeah, okay.
Or it's not so important because if you just take psi 0 or psi time evolved, well, it depends. It could be, in fact, the same up to unitary because you just apply the time evolution unitary. But for the TPS, it depends. But yeah, think of it as the wave function of the universe, or think of it if you want to be like more concrete in a lab. You have one system, closed system. You do experiment on it, and you have the initial state, for example, or it could be a ground state, whatever. But the question is, which kind of structures can determine which other kind of structures? But yeah, think of psi as the state of your system. So yeah, we don't have time to go through the proof. If you want to know the ideas, just feel free to ask a question. But some comments on the theorem. First, it's just a proof of principle that H and psi is enough structure to determine a TPS. We might like to have a property more physically meaningful. So in short, the property we have is imposing the von Neumann entropies of all the vectors with respect to a TPS, to the TPS. And well, imposing so many phenomenal entropies. Well, of course, it's physically a phenomenal entropy has a physical meaning, but still, K locality was more appealing. You were just saying the Hamiltonian should be simple, and that was kind of cute. Can we find a better P? I don't know, but at least it's possible, and it contradicts Christie's claim. Yeah, so there are some clear big links to the quantum marginal problem, a famously hard problem in quantum mechanics, but let's not dwell on that. And we in fact so the number of the complete set of invariants we have found to select the TPS is not finite, but it can be countable at least. Is it possible to react the assumption? Clearly not entirely, but it's not so clear. Anyway, now last slide. So let's collect everything together again. What are the main contributions of our paper? First, we clarify the widespread misinterpretation of Cotler as theorem. And we hope that it might help to build now new models of emergence of space-time without the misuses that may have existed before. And dissolve the apparent tension with Stoica theorem. They are just not talking about the same notion of uniqueness. Which one is the good notion of uniqueness? We argue that this is the relational uniqueness. That should be interesting. We formalized in a very general way the notion of emergent structure and this notion of relational uniqueness in the terms of geometrical invariant theory. And then we applied, and so it helped us, so this proposition that I said was very important, helped us to understand how do structures see each other in the geometrical space. And then back to the first motivation of the TPS, of the HSF question, we showed that indeed, H and psi is enough to select a preferred TPS relationally, correcting one of Stoica's claims. And now some open questions.
When you say that H and psi is enough, then what Cotler et al. Said?
Cotler do not use psi.
So it's different.
So it's completely different mathematical questions. Yeah. So this is a completely different mathematical question. When you ask, can you find a property that determines the product kind Hermitian TPS, and the same with Hermitian state TPS? It's completely different equivalence relation. And you look at our proof and Cotler's proof, nothing to do. It's completely different mathematics. And in fact, their proof was much more difficult, I'm not saying. But so some questions, open questions. So it seems to be really hard in general to find a property that determines a product kind. So just look at Cotler's proof. They found that K-locality works, but I mean, it's 20-30 pages of hardcore algebraic geometry and whatever. And our proof, I mean, it's not as hard, but still, I mean, it was a few ideas were required. And so does there exist in general, given two kinds of structure, a general recipe, or really do we have to be on case-by-case basis each time, look at the very specific nature of the structure involved? I think so, but I'm not sure. How to relax? Yeah, this is very important. When you want to say, look, I will explain the emergence of subsystems and locality in the universe, blah blah blah, just from basic quantum ingredients. But if you have to specify at first the number of subsystems that you want, a finite one, more, and their respective dimensions, it's clearly undesirable. For even especially for an Everettian who wants to see everything emerging from nothing. If you know in advance with the number of subsystems, or you really think that everything is a qubit, is made of qubits, and so all the DIs are true, why not? But by the way, it's an assumption of Cotler's proof. Okay. Now, last slide. Now we go really even further and try to show how this formalism could be extended way beyond quantum mechanics, possibly. So we started with consideration just from HSF, quantum mereology, and we ended up with a very general formalism that works in any geometrical space. Why? So all the time in this talk, for practical reason, I was using the geometrical space of the Hilbert space and the unitary group acting on it, because this is the framework of quantum mechanics. But in fact, I could replace everywhere this H, U of H by another set on which a group acts, and it would work. And Felix Klein, and so back in the end of the 19th century, was trying to unify the different geometries existing at his time, and his view, which is still very highly influential today, was that geometry is just a set and a group acting on it, and the intrinsic geometrical things arise from this quotient. So, for example, scalar products, are just intrinsic properties when your E is H and your G is U of H. But now, physics is just about geometry, all about geometry, all fundamental theoretical physics. Why? By quantum mechanics, so it's complex scalar products in Hilbert spaces plus the canonical extension to the TPS of this scalar product. But special relativity is just different Lorentzian geometry, just like general relativity, and QFT is just fiber bundles of operators over a Lorentzian manifold. So it's just all about geometry. And what if we try to use this proposition, the commutative diagram, with now M and the diffeomorphism of M, which is GR? So for example, the question you can ask is, how does a word line seize a metric, right? Or how does a light cone seize, and you see a metric or whatever. And so this part I think is important. Selecting this is something maybe that makes me love physics. When physicists are able to say this was the only possible theory, thanks to an argument. For example, Einstein's tensor is the only possible tensor you can write that is consistent with being conserved in time and symmetric and whatever. So the only possible tensor you could possibly equate with T mu nu. And that's why the Einstein equation is the only possible one somehow. The quantum fields, they are just the only possible object you can build that transform correctly under the Poincaré group. So you have almost no choice. This is how Weinberg presents the quantum fields. I think it's much more satisfying for a mathematician. Schrödinger equation, it's the only possible equation that is Markovian and compatible with the Hilbert space structure. Then you have the variety of operational reconstruction attempts of quantum mechanics. So you really reconstruct the Hilbert space, saying that it's the only possible structure such that, blah, blah, blah. And bosonic and fermionic statistics. So showing that there are no parastatistics, no more exotic way statistical particles. Well, recently a group of people from Vienna, but I mean there are plenty of other works, but managed to select boson and fermions and exclude all the rest out of one principle, which is the global covariance principle, global permutation. I don't remember how they call it, but they have two proposals of anyway. And now it seems to connect with QRFs. I don't know how people here in the room are familiar with quantum reference frames, but the map pi is 0. So in this proposition, which I called from third person to first person perspective, it was on the slide before. This map, this bijection between the orbits and the quotients, temptingly reminds the so-called reduction map in QRF, which is a map moving from what they call the perspective neutral frame. So the third person point of view, we could say, and moving to the first person point of view of one reference, one structure, one whatever. And this map looks very much the same. And so can our formalism be used in the field of QRF fruitfully? I don't know. We can perhaps even dream that it could help unify the different approaches, because so far it's really like it's a zoo of approaches, and it's not so clear today what are the links between them. And yeah, thank you for your attention very much.
Aslav Bruckner is asking a question.
So should I?
Is your computer unmuted?
Wait. Yes.
Hello, do you hear
Hello,
me?
yeah, I hear you.
Okay.
So thanks a lot for the talk. I enjoyed it much.
Thank you.
I have a question just about clarification. You might even mention this, and I overlooked this. Is Cotler et al. Proof is the proof not of the existence of the k-local TPS in which we have a Hamiltonian k-local, but if this exists,
Yep.
then there is no k-dual.
Yeah,
Am I right? Okay. And your proof,
Correct.
is it, I overlook, is it of the same type or it's also a proof of existence?
excellent question. So thank you very much, because I can talk about a few things I didn't have time. So I will try to reply properly.
You should share yours.
I don't share anymore. Do I share now? Sorry, share. Okay. Good. Normally I share now.
Yes.
So yes, this. Yeah, on this slide.
Repeat the question.
Yeah. So I will repeat the question and try to answer. Cotler's. So sometimes I felt it when I said something. It was a little bit abused, because sometimes I was saying that you can construct a TPS via Cotler's theorem. It's entirely false. In fact, you can, if it exists, it is unique. But it doesn't give you like a constructive method to build a TPS, not at all. And so Czeslav's question is it the same for us? We select a unique TPS, but can we really construct it? And so it's linked. So our unitary invariant property is to impose the list of all of the entanglement entropies. So the fundamental entropies, for example, of all vectors with respect to a TPS, and we say this is unique. This characterizes the TPS. But then the question is, if you give me a list of entanglement entropies, can I really realize that? Is there really a TPS that corresponds to this super long abstract list of entropies? And the answer of this question is the quantum marginal problem. So it's famously hard. It's I think an NP hard problem. What is the quantum marginal problem? It's the question: give me a list of partial states. Is there, and can I reconstruct the total state from which the partial traces give this list of partial states? And so it's very hard in general. And so now I can give the answer to a question, Czeslaw. We are exactly like Cotler. We do better, because you should be because when you impose a list of fundamental entropies, you never know if there is really a TPS that realizes that. And another example I could say, yep.
I mean, there is a finance. I ask actually a little bit less than construction. I ask for proof of existence, but of course, construction is also very interesting.
Yeah, but so the proof of existence is let me phrase it again, because not all unitary invariant properties that you could write down, like as we do, like imposing the fundamental entropies of everyone, not all correspond to an actual TPS. Another example, maybe simpler one, is look at this determined kind of n vectors. If you have n vectors, and then you say I impose the pairwise scalar products, so I impose the Gram matrix. Yeah, but only the semi-definite positive matrix, Hermitian matrix, will really correspond to a family of n vector. If you have another crazy matrix which is not Hermitian or positive or whatever, then you have no chance that the mutual pairwise scalar product correspond to this matrix. So here in this case, it's very easy to know what are the values to ask for which correspond to an actual structure. It's the set of Gij which are positive semi-definite. In our case, determining the set of the list of entropies that correspond to something truly realizable, there's no simple answer, just as a Hermitian matrix, positive matrix. And the answer is the quantum marginal problem. But so we know we don't construct it. Our proof is just based on if there is a TPS, then it is unique, just like Cotler do.
Thank you.
Do we have any more questions?
Maybe I should.
No, I muted.
Inside the room?
Oh, can you tell us a bit more about your proof? Just the
Yeah,
outline of the main idea.
sure. But you see, it's not that terrible. So do I still share the screen? You see online? No, maybe not now. Wait. So here's the proof. So apply the corollary. So by the corollary before, the corollary of the commutative diagram, in the case of a free transitive and free action, you can fix h and psi. So this is the S0 we move to, right? We move to the perspective of h psi, and we are looking for a property such that it holds for exactly one t. And now, in an absolute sense, because we are these special cases, now we can be absolutist. And if we find such a t, we are done. Now, an important thing to observe is that L of h, the set of operators, has an inner product. So you have a multiplication. And therefore, h psi generates a very big structure because you can take all polynomials of h and apply them to psi. When you had only h, well, you can't build much. When you have only psi, you can't build much. You have only your psi. When you have h of psi, h and psi, by acting them together, you can generate a huge thing because you could generate all the f of h of psi for f a polynomial or even a continuous function. And then this f of h of psi, it turns out that it's everyone. If the spectrum is non-degenerate and psi has no vanishing eigenprojection on h, but apart from that, you generate everyone. You can attain any vector by acting with a proper polynomial of h on psi. Therefore, you can, in a unitary invariant way, label all the vectors in h in a unitary invariant way, just by saying this is the vector associated to h and psi through the polynomial, this polynomial, which is absolutely, independent of your reference or your unitary or your coordinates in h. Now you define the property P as imposing the values of the fundamental entropies with respect to the TPS of all these f of h of psi, but it means to everyone. So you can really impose the fundamental entropy. So imagine you have a super long list of numbers between 0 and 1, but each of them are labeled by a polynomial. So each of them should correspond to a well-defined vector, which is the f of h of psi, and it should be the entanglement entropy of this one. Or let's say, yeah, all the partial traces of this one. And now suppose this property P suppose it holds for two triplets. And let's show that in fact T equals T prime. So there exists a unitary mapping T to T prime, even though T and T prime are different, because two TPS are entirely defined by a properly labeled orthonormal basis. So you can already, because TPS is a determined kind. There is only one TPS once you fix the number of factors I said before. So let's call U this unitary mapping T to T prime. Then the fact that the property holds for the two triplets is equivalent to the fact that with respect to T, U maps product state to product state. Maybe it's not immediate to see it, but if you impose the entanglement entropies of everyone in T, and if they are the same in T prime, and if you have a unitary mapping T to T prime, in fact, this unitary, with respect to only T, preserves the phenomenal entropies. So it maps all the phenomenal entropies to vectors which have the same phenomenal entropies. In particular, the product states, they are characterized by the fact that they have 0 phenomenal entropy on every partial state. And so this unitary, mapping T to T prime, has the property of mapping product state to product state in T. And then you just have to prove a little lemma showing that if you have an operator mapping pure tensors to pure tensors, in fact, it's a product of local operators. Not so hard to prove. And so you conclude, because then this unitary is a product of local unitaries. Therefore, T equal T prime, because remember, TPS is an equivalence class of such local operators. And so if T equal T prime, well, look again at the first line. This is exactly what we had to show. We have found a P that holds for exactly one T. And that's good. We're done. Yeah.
Follow-up question. So earlier we asked, like, is psi an ground state or an eigenstate of H? So it seems the proof requires that it is not an eigenstate, right?
Ah, true. True. You're right. Perfectly right. And it's still an open question to know how we can relax the assumption. So for sure, you cannot have the spectrum to degenerate, because if, suppose, extreme case, H is the identity, then f of H of psi is just psi. You generate, maybe the complex line, the complex plane, but it's just psi. You generate nothing. So for sure, you will not grasp enough vector so that you can apply this lemma, or maybe a stronger version of this lemma. And it's the same for the eigenprojection, because if, let's say psi is the ground state, f of H of psi will generate almost nothing again. So clearly we're not grasping enough. So it seems to be a very hard question and open, but not so interesting, but very hard.
Good combination.
So don't do it, but unless you really don't know what to do. So yeah, what exactly is the weakest assumption I need on H and psi to generate enough vector so that it constrains sufficiently this unitary U,
Yeah. But I guess a universe where we are just staying in the ground state is quite boring.
Probably. Probably. Yeah.
Somehow this whole thing, when you talk about that you can label all the psi's, this goes very close for me to model theory and definability.
This is very close. That's why I enjoyed so much this work.
This is it.
Invariant, already invariant theory in geometry, invariant theory. I was mentioning this again. So is really close to category stuff and also model theory and so on. And so we are really close here. In hidden everywhere, there is this notion of, because the vectors in H, they exist anyway. So you could say I could just impose the Feynman entropies of everyone as I wish. So why this argument with the polynomials and whatever? Because you need to refer to them, to label them, coordinate independently or something. And this is this is very much about, as I said, model theory and how structures, how syntax generates structures.
What is definable?
Yeah, what is exactly this? And that's why also it's really hard sometimes to explain the results. Even ourselves in the group, sometimes we were chatting and suddenly one of us was like, I'm not sure anymore what we're doing, but now I'm really sure it's true. But yeah, it's really hard sometimes to grasp. And also this notion of, why the two problems are so different, like Cotler's theorem and ours. Whereas you just add up psi, but no, nothing to do.
Yeah. I guess since there are no more questions online.
Yeah. Thank you very much.
Thank you.
Thank you.